February 1945, Iwo Jima. A reinforced concrete bunker sits embedded in volcanic rock, firing ports barely visible through the smoke and dust. Inside, Japanese defenders have endured 3 days of naval bombardment and artillery fire. The concrete is scarred but intact. They have ammunition, water, and orders to fight to the last man. A Marine infantry company has tried twice to take the position. Both attempts ended with casualties piling up on the black sand. Rifle fire cannot reach the gunners. Grenades bounce off the concrete. Even satchel charges only chip the surface. The bunker has to fall, but nobody knows how to make it happen. Then something new appears through the smoke. An M4 Sherman tank, but different. No cannon report. No shell impacts. Instead, a lance of liquid fire erupts from the turret, a stream of burning gel that bends against the wind and pours directly into the firing port. For 3 seconds, the flame holds steady. When it stops, the bunker is silent. The Marines advance. Nobody inside survived. The weapon that killed them was not a flamethrower. It was a flamethrower tank, and it changed how America fought the Pacific War. The tank looked almost ordinary. Standard M4 Sherman hull, familiar silhouette, regulation olive drab paint. But where the 75mm main gun should have been, there was something else, a flame projector, and in place of ammunition racks, 290 gallons of jellied gasoline waited under pressure. American tankers called it the Zippo after the lighter brand. Unofficial nickname, perfect accuracy. One squeeze of the trigger and you had fire. Lots of fire. Fire that stuck to whatever it touched. Fire that burned at temperatures exceeding 2,000 degrees Fahrenheit. Fire that did not care about concrete, steel, or the laws of conventional warfare. By any measure of civilized warfare, the flamethrower tank was horrific. It killed in ways that violated every instinct about honorable combat. It burned men alive. It consumed oxygen and left defenders suffocating in smoke. It created psychological terror that went far beyond its tactical capabilities. It was also one of the most effective weapons the United States deployed in the Pacific Theater. Marines who fought on Iwo Jima, Okinawa, and throughout the island campaigns would later state plainly, "The Zippo saved American lives. Lots of American lives." The math was brutal but simple. Every Japanese position that surrendered or evacuated because of flame meant fewer Marines charging machine gun nests. The flamethrower tank represented American engineering solving an impossible tactical problem. The problem was how to kill determined defenders in fortified positions without losing entire companies of infantry in the process. The solution was to make those fortifications uninhabitable, not through explosive force, but through heat, smoke, and the primal human terror of burning alive. If you're finding this interesting, hit that subscribe button. It helps more than you know, and drop a comment below telling us where you're watching from. Now, let's dive into why this weapon was so desperately needed. To understand why the United States needed flamethrower tanks, you have to understand what fighting looked like in the Pacific Theater by 1944. The Japanese had abandoned any hope of winning defensive battles through firepower. Instead, they perfected fortification. On islands like Peleliu, Iwo Jima, and Okinawa, Japanese forces transformed natural caves and volcanic rock into interconnected defensive networks. Bunkers featured reinforced concrete walls 3 to 5 feet thick. Firing ports were narrow slits that exposed almost nothing to counterfire. Entrances were positioned to create overlapping fields of fire. Entire companies of defenders could disappear underground, connected by tunnels that allowed them to relocate between positions. American doctrine had no answer for this. Artillery bombardment, which had worked in Europe, proved almost useless. Naval gunfire from battleships could crater the surface, but rarely penetrated deep enough to collapse the fortifications. Even direct hits from 16-inch shells sometimes left bunkers structurally intact, with defenders shaken but alive and ready to resume firing. Infantry flamethrowers existed, but they created as many problems as they solved. The M1A1 flamethrower, standard issue by 1943, weighed 68 pounds fully loaded. It had an effective range of about 20 to 25 yards. That meant the operator had to get dangerously close to the target, often crossing open ground under fire. The fuel tanks were conspicuous. Japanese defenders quickly learned to target flamethrower operators first. Casualty rates among flamethrower troops were catastrophic, sometimes exceeding 50% in sustained combat. The tactical problem was straightforward but seemed impossible to solve. American forces needed to neutralize fortified positions without sacrificing infantry. They needed to project flame at longer ranges from protected positions with enough fuel capacity to engage multiple targets. They needed the psychological impact of flamethrowers combined with the armor protection and mobility of tanks. The specification seemed contradictory. Flamethrowers required pressurized fuel systems, complex ignition mechanisms, and substantial fuel capacity. Tanks required armor, mechanical reliability, and the ability to operate in rough terrain. Combining them meant creating a vehicle that could withstand enemy fire while carrying hundreds of gallons of flammable fuel. One penetrating hit could turn the entire tank into an incinerator, killing the crew instantly. Chemical Warfare Service engineers looked at the problem and understood the stakes. Every week without a solution meant more Marines dying on beaches. The Japanese were not going to surrender. They were not going to evacuate. They were fortifying harder. Without a weapon that could make bunkers untenable, the final battles of the Pacific War would become grinding campaigns of attrition, measured in American casualties, numbered in thousands per island. The question was not whether to build a flamethrower tank. The question was how to build one that worked. The development of the American flamethrower tank was not a single breakthrough, but a series of incremental innovations, each solving a specific engineering challenge. The Chemical Warfare Service began experimenting with mechanized flamethrowers in 1942. Early attempts involved mounting existing man-portable flamethrowers on jeeps and half-tracks. These proved unsatisfactory. The vehicles lacked armor, making them death traps in combat. The flamethrowers themselves had insufficient range and fuel capacity. What the military needed was not a flamethrower on a vehicle, but a vehicle designed from the beginning as a flamethrower delivery system. The breakthrough came with the decision to use the M4 Sherman as the platform. The Sherman was already proven in combat. It had adequate armor, mechanical reliability, and was being produced in massive quantities. Modifying existing tanks would be faster and cheaper than designing an entirely new vehicle. But mounting a flamethrower in place of the main gun created immediate problems. The first was fuel. Standard flamethrower fuel, gasoline thickened with rubber or latex, was volatile and difficult to control. It burned quickly, but lacked the range needed for tank-mounted operations. The solution came from research into napalm, a mixture of gasoline and a powder made from naphthalene and palmitate. Napalm had three critical properties. It was thicker than gasoline, allowing it to be projected farther. It stuck to surfaces rather than running off, and it burned hotter and longer than conventional flamethrower fuel. The fuel system itself required significant innovation. The tank needed to carry enough fuel for sustained operations, at least 12 to 15 seconds of continuous flame, ideally more. Engineers settled on two fuel tanks with a combined capacity of 290 gallons, mounted in the hull where ammunition would normally be stored. A pressurization system using compressed nitrogen forced the fuel through armored lines to the flame gun mounted in the turret. Working pressure reached approximately 300 psi, enough to project flame 100 to 150 yards under optimal conditions. The flame gun replaced the Sherman's 75mm main cannon. It was not simply a larger version of the infantry flamethrower. The flame gun featured a three-stage system: ignition, projection, and sustained flame. At the muzzle, an electric igniter created a pilot flame. When the operator pressed the trigger, Pressurized fuel flowed through the gun and ignited on contact with the pilot flame. The result was a continuous stream of burning gel that maintained coherence over surprising distances. Engineers obsessed over ignition reliability. In combat, a flamethrower that failed to ignite was worse than useless. It marked the tank as a high-value target without providing any offensive capability. The solution involved redundant ignition systems, multiple electric igniters, backed up by chemical ignition cartridges that could be fired manually if electrical systems failed. Testing showed ignition reliability exceeding 95%, even in adverse conditions like rain or heavy dust. Armor protection for the fuel system was non-negotiable. The engineers understood that a penetrating hit to the fuel tanks would be catastrophic. They installed additional armor plating around fuel lines and tanks, accepting the weight penalty. Total combat weight of the flamethrower Sherman increased to approximately 35 tons, about 2,500 pounds heavier than a standard gun tank. The weight affected maneuverability slightly, but not enough to compromise operational effectiveness. The final innovation was tactical flexibility. The flamethrower turret retained a secondary armament, a 30 caliber machine gun for anti-personnel work and a 50 caliber machine gun on the turret top for air defense and suppression. This allowed the tank to engage multiple target types without relying solely on flame. In practice, tank commanders often used the machine guns to suppress defenders before employing flame, maximizing psychological impact. Three main variants emerged from development. The M4A3R3 Zippo became the standard Pacific Theater model, featuring the flame gun in the turret with full traverse capability. The POA CWS H1, developed by Pacific Ocean Areas Command, mounted the flame projector in the bow, replacing the bow machine gun. This variant was simpler to produce but had limited traverse. A third variant, the POA CWS H5, represented the ultimate evolution, combining bow-mounted and turret-mounted flame projectors for maximum flexibility. Field testing occurred at locations including Schofield Barracks in Hawaii and Camp Pendleton in California. Marine and Army units practiced assaulting mock bunkers using concrete and steel to simulate Japanese fortifications. The tests revealed both capabilities and limitations. Flame could not penetrate solid concrete, but it could enter any opening larger than a few inches. A 3-second burst into a bunker created conditions incompatible with human survival. Temperatures inside reaching 500 to 1,000 degrees Fahrenheit within seconds. The weapon worked. Now it had to prove itself in combat. Production of flamethrower tanks began in earnest in late 1944. The Chemical Warfare Service contracted multiple facilities to handle conversions. Standard M4 Sherman tanks were pulled from production lines and sent to specialized workshops where technicians removed the main gun, installed fuel systems, and integrated flame projectors. Numbers remain somewhat unclear due to wartime record keeping, but estimates suggest approximately 800 flamethrower tanks were produced across all variants between 1944 and 1945. The M4A3R3 accounted for the largest portion, with around 600 units. The POA, CWS H1, and H5 variants accounted for the remainder, with exact figures disputed among historians. Training programs emphasized the unique characteristics of flamethrower tanks. Tank crews learned that their vehicle was a priority target. The moment enemy forces identified a Zippo, fire intensified dramatically. Japanese forces understood that destroying a flamethrower tank eliminated one of the most dangerous weapons on the battlefield. Crews practiced rapid deployment, quick flame bursts, and immediate withdrawal to minimize exposure. The psychological aspect of training proved almost as important as the technical. Operating a flamethrower tank meant accepting that your weapon killed in horrific ways. The Marine Corps did not sugarcoat this. Instructors explained that flame created suffering, that the weapon violated instincts about honorable combat, and that the men using it would have to live with that knowledge. The justification was pragmatic. Flamethrowers ended battles faster and with fewer American casualties than alternatives. Logistics for flame operations required careful planning. Each tank carried enough fuel for 12 to 20 seconds of continuous flame, depending on pressure settings and fuel mixture. In practice, crews fired in short bursts, typically 3 to 5 seconds each, conserving fuel across multiple engagements. Refueling required specialized equipment and trained personnel. Forward supply units carried napalm in drums, along with compressed nitrogen cylinders for the pressurization system. Initial deployment to combat zones occurred in late 1944 and early 1945. The first flamethrower, Shermans, reached Saipan, where they participated in mopping up operations against remaining Japanese holdouts. Performance reports were enthusiastic. Tank commanders reported that flame bursts of 3 to 4 seconds were sufficient to clear most fortified positions. Some bunkers surrendered after seeing the flame without actually being hit, defenders choosing captivity over burning. Tank crews initially approached the Zippos with skepticism. The idea of removing the main gun seemed counterintuitive. Tankers trained to rely on the 75mm cannon for direct fire support. Trading explosive shells for flame felt like a downgrade. Combat experience changed those opinions rapidly. Tank commanders discovered that flame was more effective than high explosive against the reinforced positions dominating Pacific battlefields. By early 1945, flamethrower tanks were integral to American offensive doctrine in the Pacific. Assault plans specifically incorporated Zippos for bunker reduction. The standard tactic involved combined arms. Infantry would identify and mark fortified positions, conventional gun tanks would suppress enemy fire, and flamethrower tanks would move forward under covering fire to deliver flame into openings. The weapon that had seemed experimental in 1944 had become essential by 1945, and the battles ahead would prove just how essential it was. The flamethrower tank proved its worth in combat repeatedly, nowhere more dramatically than on Iwo Jima. February 19, 1945. The invasion of Iwo Jima began with what Marines expected, a nightmare. Japanese defenders had spent months fortifying the island, creating a defensive network of astonishing complexity. More than 11 miles of tunnels connected over 1,500 defensive positions. Bunkers featured reinforced concrete and volcanic rock, some with walls 8 feet thick. The Japanese commander, General Tadamichi Kuribayashi, had ordered defenders to abandon the traditional banzai charges and instead fight from fortified positions to maximize American casualties. Early assaults confirmed the worst predictions. Marines landed and immediately faced withering fire from positions they could barely see. Artillery had failed to destroy the bunkers. Naval gunfire had barely scratched them. Infantry flamethrowers could not get close enough without prohibitive casualties. Progress was measured in yards, purchased with Marine lives. The Zippos arrived on February 24th, 5 days into the battle. The 5th Tank Battalion included multiple flamethrower Shermans, and tank commanders immediately understood their value. The first significant engagement occurred near Airfield No. 1, where a complex of bunkers had stopped the Marine advance cold. Conventional Shermans had fired dozens of 75mm shells with minimal effect. The bunkers were simply too well built. A flamethrower tank moved forward, accompanied by infantry providing covering fire. The tank approached to within 50 yards of the nearest bunker, turret traversing to align the flame gun. The commander ordered a burst. 3 seconds. The stream of burning gel arced across the volcanic ash and poured into the bunker's firing port with horrifying precision. Flame filled the interior, consuming oxygen and creating temperatures incompatible with survival. When the flame stopped, the bunker was silent. The same pattern repeated across the battlefield. Bunkers that had resisted days of bombardment fell to seconds of flame. Japanese defenders faced an impossible choice: remain in fortifications that had become ovens, or evacuate into the open where Marines could engage them directly. Most chose to evacuate. Some chose surrender. Some chose to fight until the flame found them. Sergeant Robert Henderson, a flamethrower tank commander with the 4th Marine Division, later described the experience in a letter preserved in the National Archives. He wrote, "You could see them running out of those caves, uniforms on fire, and you knew what you had done. It wasn't clean. It wasn't honorable. But it worked, and it meant my friends weren't getting shot trying to rush those positions with grenades and rifles. I don't know if that makes it right, but that was the choice." The battle for Hill 382, later known as the Meat Grinder, demonstrated the flamethrower tank's effectiveness in complex terrain. Defenders had fortified the hill with dozens of interconnected positions. Conventional attacks had failed repeatedly. Flamethrower tanks, operating in teams with infantry and gun tanks, systematically cleared positions over a week of fighting. Tank commanders learned to coordinate flame bursts, with one tank engaging while another moved into position. The tactics evolved in real time, refined by the harsh necessity of combat. Okinawa, the next major campaign, saw even greater integration of flamethrower tanks into assault doctrine. The invasion began April 1st, 1945, and quickly devolved into brutal fighting as Japanese forces withdrew to fortified positions in the island's southern highlands. The terrain favored defenders. Steep ridges, narrow valleys, caves, and tombs transformed into bunkers. The 713th Tank Battalion, equipped with both gun tanks and flamethrower variants, led the assault on the Shuri Line, the main Japanese defensive position. Lieutenant Colonel Edward Snedeker commanded the battalion and understood the limitations of conventional weapons against prepared defenses. His after-action report, preserved at the National Archives, details the systematic use of flame to reduce fortified positions. One engagement exemplified the tactic. A ridgeline position had stopped the advance for 3 days. Artillery, airstrikes, and naval gunfire had all been employed, with minimal results. Snedeker ordered 4 flamethrower tanks to approach under covering fire from infantry and gun tanks. The flamethrowers advanced in pairs, one firing while the other moved. They reached effective range and delivered sustained flame bursts into cave openings along the ridge. Within 20 minutes, the position that had resisted 3 days of bombardment was silent. The psychological impact of flamethrower tanks extended beyond their immediate tactical effect. Japanese troops who witnessed flame attacks reported them to their commanders in language revealing genuine terror. Intelligence officers analyzing captured documents noted repeated references to fire tanks and recommendations to target them immediately. Orders from Japanese commanders emphasized destroying flamethrower tanks before they could deploy, indicating the weapon's effectiveness had been recognized at the highest levels. But the weapon was not without cost. Tank crews operating Zippos faced unique dangers. The fuel tanks, despite armor protection, remained vulnerable. A direct hit from anti-tank weapons could penetrate the hull and ignite the fuel. When that happened, the result was catastrophic. The entire tank became an inferno, crew survival nearly impossible. Records indicate that flamethrower tanks suffered higher loss rates than conventional gun tanks, though exact figures vary by source. The ethical implications troubled some commanders and crews. Flamethrowers killed in ways that seemed excessive even by the brutal standards of the Pacific War. Critics within the military questioned whether the weapon violated principles of humane warfare. Defenders pointed to the casualty statistics. On Iwo Jima, Marine casualties exceeded $26,000, with nearly 7,000 killed. Without flamethrower tanks, those numbers would have been substantially higher. The brutal mathematics suggested that weapons that shortened battles ultimately saved lives, American and Japanese both. The flamethrower tank also proved valuable in urban combat, though this represented a smaller portion of operations. On Okinawa, fighting in Naha and Shuri required clearing buildings and fortified structures. Flamethrower tanks could project flame into buildings from standoff distances, forcing defenders out without requiring infantry to clear each room. The tactic was effective, but carried risks of collateral damage, particularly to civilian structures. Throughout the campaigns, flamethrower tank crews developed informal expertise. They learned that certain bunker designs were more vulnerable to flame than others. Positions with single entrances were death traps once flame entered. Defenders had no escape route. Positions with multiple openings allowed defenders to evacuate, but this suited American tactics as well, forcing defenders into the open where they could be engaged by conventional weapons. The weapon that had been experimental in 1944 had become indispensable by mid-1945. Plans for the invasion of mainland Japan, Operation Downfall, scheduled for November 1945, included hundreds of flamethrower tanks. Planners anticipated Japanese defenses even more formidable than those encountered on Iwo Jima and Okinawa. The Zippo would have been central to American assault doctrine. The atomic bombings of Hiroshima and Nagasaki and Japan's subsequent surrender meant Operation Downfall never occurred. The flamethrower tanks never faced the ultimate test their designers had anticipated, but their combat record in the Marianas, the Philippines, Iwo Jima, and Okinawa had already proven their worth. The American flamethrower tank was not unique. Other nations developed similar weapons, though design philosophies and operational doctrines differed significantly. The British Churchill Crocodile represented the most sophisticated Allied flamethrower tank. Unlike the American Zippo, which integrated the fuel system into the tank hull, the Crocodile towed a single-wheeled armored trailer containing 400 gallons of fuel. The fuel trailer connected to the tank via armored lines, feeding a flame projector that replaced the hull-mounted machine gun. The system offered advantages and disadvantages compared to the American design. The Crocodile's advantage was fuel capacity. With 400 gallons versus the Zippo's 290 gallons, the British tank could sustain flame longer or engage more targets per mission. The pressurization system, using nitrogen stored at 350 psi, provided effective range of approximately 120 yards, comparable to or slightly exceeding American capabilities. The Churchill's heavy armor, substantially thicker than the Sherman's, offered better crew protection, but the trailer created problems. It limited maneuverability, particularly in rough terrain or urban environments. The armored fuel lines connecting tank to trailer were vulnerable to enemy fire or obstacles. If damaged, the entire system became inoperable. The trailer also made the Crocodile more visible and identifiable, marking it as a high-value target. The American integrated system sacrificed fuel capacity for mobility and simplicity. The Zippo could maneuver as freely as any Sherman, navigate terrain that would immobilize a trailer, and maintain full combat effectiveness even in confined spaces. For the Pacific theater, where terrain frequently included jungles, volcanic rock, and narrow beaches, this proved decisive. The British employed Crocodiles primarily in northwest Europe, where terrain was more accommodating to the trailer system. In that environment, the Crocodile proved highly effective, particularly in reducing fortified positions during the Battle of Normandy and subsequent operations. British commanders praised the weapon's ability to clear bunkers and pillboxes that resisted conventional assault. German flamethrower tank development lagged significantly. The Wehrmacht produced small numbers of experimental flamethrower variants, most based on the Panzer III chassis or captured vehicles. None achieved the production scale or operational integration of Allied systems. Several factors explain this disparity. First, German tactical doctrine emphasized defensive operations and mobile warfare, particularly in the early war years. Flamethrower tanks are primarily defensive reduction weapons, more useful for clearing fortifications than for rapid advances. By the time defensive operations became Germany's primary concern, industrial capacity and resources had been severely degraded. Second, Germany faced fuel shortages that made operating napalm-burning vehicles impractical. Every gallon of flamethrower fuel was a gallon not available for aircraft or conventional tanks. The resource allocation favored weapons with higher mobility and multi-role capabilities. Third, German engineers never fully solved the integration challenges. Attempts to mount flamethrowers on Panzer IIIs and Stujik assault guns resulted in vehicles with inadequate fuel capacity or limited traverse. The weapons were unreliable and saw minimal combat use. Japanese forces developed no flamethrower tanks, despite facing the American weapon repeatedly. This absence reflects strategic decisions and industrial limitations. By 1944-1945, Japanese industrial capacity was collapsing under American bombing and resource blockades. Developing and producing a complex weapon system like a flamethrower tank was beyond available resources. The comparative assessment reveals that the American flamethrower tank, despite its apparent simplicity compared to the British Crocodile, was optimized for its operational environment. The Pacific Theater demanded mobility, reliability, and the ability to operate in extreme terrain conditions. The M4A3R3 Zippo delivered those capabilities while maintaining the psychological and tactical effectiveness that made flamethrower tanks valuable in the first place. Specifications tell the story clearly. The American system achieved 100 to 150 yard range with a 290-gallon fuel capacity, providing 12 to 20 seconds of flame in a platform that retained full Sherman mobility. The British system achieved slightly better range with greater fuel capacity, but sacrificed maneuverability. The Germans never fielded a comparable weapon at scale. The Japanese had no equivalent. The American flamethrower tank succeeded because it matched weapon characteristics to operational requirements. Pacific fortifications required flame. Pacific terrain required mobility. American industry could produce the weapon in useful numbers. The combination of these factors made the Zippo perhaps the most effective flamethrower tank of World War II, measured not by technical sophistication, but by operational impact. The flamethrower tank, for all its effectiveness, was far from a perfect weapon. Limitations were numerous, some technical, some operational, some psychological. Fuel capacity constrained operations. Even the 290-gallon tanks provided only 12 to 20 seconds of continuous flame. In practice, this translated to perhaps 4 to 6 effective bursts of 3 to 5 seconds each. Tank commanders had to prioritize targets carefully. Once fuel was expended, the Zippo became significantly less valuable, reduced to its secondary machine gun armament until it could withdraw and refuel. Refueling was dangerous and time-consuming. The process required specialized equipment, trained personnel, and relative safety from enemy fire. Forward refueling points became vulnerable targets. Japanese forces learned to target supply areas where flamethrower tanks refueled, hoping to destroy fuel stockpiles or catch tanks in vulnerable conditions. The fuel tanks themselves, despite armor protection, represented an existential vulnerability. Anti-tank weapons that penetrated the hull could ignite the fuel, creating catastrophic fires. Tank crews understood this risk. Some developed superstitious rituals about checking armor and avoiding unnecessary exposure. The psychological burden of operating a vehicle filled with hundreds of gallons of flammable gel affected crews in ways that manifested differently than conventional combat stress. Weather and terrain imposed limitations. Rain reduced flame effectiveness by cooling the fuel stream and dispersing the burning gel. Heavy rain could prevent ignition entirely, though the redundant ignition systems minimized this risk. Mud and rough terrain, ubiquitous in the Pacific Theater, restricted mobility and made precise positioning difficult. Dense jungle sometimes obscured targets until the tank was dangerously close, negating the range advantage over infantry flamethrowers. Maintenance demands exceeded those of conventional gun tanks. The flame gun required regular cleaning to prevent carbon buildup. The ignition system needed inspection after every operation. The pressurization system developed leaks that required immediate repair. Fuel lines corroded when exposed to salt water or tropical humidity. Tank battalions operating Zippos required additional mechanics with specialized training. The ethical implications troubled many involved. The flamethrower killed in ways that seemed uniquely cruel. Burned bodies recovered from cleared bunkers showed the weapon's horrific effects. Some crew members struggled psychologically with the knowledge of what their weapon did. Post-war interviews reveal that operators of flamethrower tanks experienced distinct patterns of trauma different from but comparable to trauma experienced by infantry or conventional tank crews. Critics within the military establishment questioned whether flamethrowers violated international norms, though no formal prohibitions existed during World War II. The weapon generated controversy in ways that conventional explosives did not, despite arguable equivalence in lethality. The visceral horror of burning overshadowed rational assessment of whether death by flame was meaningfully worse than death by shrapnel, bullets, or blast effects. Post-war, the flamethrower tank continued in service. The Korean War saw limited use of flamethrower Shermans, primarily in bunker reduction roles similar to Pacific operations. The M67 flamethrower tank, based on the M48 patent chassis, entered service in the 1950s and saw extensive use in Vietnam. The M67 represented evolutionary improvement, better range, greater fuel capacity, improved reliability. But the fundamental concept remained unchanged from World War II designs. Modern military forces largely abandoned flamethrower tanks by the 1980s. Advances in precision weapons, thermobaric explosives, and changing international law regarding incendiary weapons reduced their utility. The 1983 Convention on Certain Conventional Weapons restricted use of incendiary weapons against civilian populations and in areas with civilian presence, effectively ending widespread military use of flamethrowers. Museum collections preserve examples of World War II flamethrower tanks. The National Museum of the Marine Corps displays an M4A3R3. The Patton Museum of Cavalry and Armor houses several variants. These machines, static and silent now, represent a specific moment in military technology when the problem of fortified defenses demanded solutions that challenged comfortable assumptions about warfare. The legacy of the flamethrower tank extends beyond the weapon itself. It demonstrated that even the most horrific weapons could be justified by casualty calculus. It showed that technological solutions to tactical problems sometimes required accepting ethical complexity. It proved that effectiveness in war is not always aligned with humanity. The crews who operated these weapons lived with that knowledge. Many struggled with it. Some found justification in the lives saved. Others carried guilt. Most simply acknowledged that war presents impossible choices, and they had done what was asked of them in circumstances none had chosen. February 1945. Iwo Jima. A reinforced concrete bunker embedded in volcanic rock. 3 days of bombardment failed to destroy it. 2 Marine companies failed to take it. Then, an M4A3R3 flamethrower tank, nicknamed Zippo, approached through the smoke and delivered 3 seconds of liquid fire into the firing port. The bunker that had seemed impregnable fell silent. American engineers had solved what appeared impossible. They created a weapon that could reduce the strongest fortifications without requiring infantry to charge machine guns. They integrated a flamethrower into a mobile, armored platform that could operate in the most hostile terrain on Earth. They produced it in numbers sufficient to affect battlefield outcomes. They did this while Japan was building defenses designed to maximize American casualties, while Marines were dying on black sand beaches, while the war's end remained uncertain. The flamethrower tank was brutal. It was horrific. It violated every comfortable notion about civilized warfare. It also saved lives, American and Japanese both, by shortening battles that otherwise would have been even more devastating. The mathematics were simple and terrible. Weapons that made fortifications untenable reduced the need for infantry assaults. Reduced infantry assaults meant fewer casualties. Fewer casualties meant more men survived to go home when the war ended. That was American engineering in 1945. That was what happened when tactical necessity collided with industrial capability. That was how you fought an enemy determined to die in fortifications designed to kill as many attackers as possible before falling. The Zippo did not win the Pacific War alone. No weapon did. But in the desperate final campaigns, on islands measured in yards of progress and thousands of casualties, the flamethrower tank gave American forces a tool that worked when nothing else did. It turned bunkers into tombs, caves into ovens, fortifications into killing grounds for their defenders rather than their attackers. History remembers the atomic bombs that ended the war. It should also remember the flamethrower tanks that fought it and the men who operated them, knowing what their weapon did and accepting that burden because someone had to, and because the alternative was worse. That was the choice. That was the weapon. That was the price of victory in the Pacific.